out on Collins. I be
Hello guys, welcome to Everything You Need. In the previous video we discussed how the PIR sensor works and the principle around it. In this video let's discuss the PIR sensor in detail. Here is the list of things that we are going to cover in this video. At the heart of the module is a passive infrared controller IC, that is BISS 0001. Because of the noise immunity it provides, this IC is one of the most stable PIR controllers available in the market. This chip takes the output from the pyroelectric sensor and does some minor processing on it to emit a digital output pulse. Coming to power, this module comes with a 3.3 volts precision voltage regulator, so it can be powered with any DC voltage from 4.5 to 12 volts, although 5 volts is commonly used because this sensor is basically used with a combination of Arduino and some other microcontrollers. And also it comes with a protection diode, also known as a safety diode, to protect the module from the reverse voltage and current. So if you accidentally connect the power with an incorrect polarity, your module will not be damaged. The PIR sensor comes with two potentiometers at the back side, one of which is for sensitivity adjustment and other is for time delay adjustment. The potentiometer that is at the left side is meant for sensitivity adjustment. This potentiometer sets the maximum detection range. Sensitivity can be adjusted over a range of approximately 3 meters to 7 meters, that is 9 to 21 feet. However, the topology of your room can affect the actual range you get. Here CW means clockwise and CCW means counterclockwise. To increase the range or the sensitivity, we have to turn around the clockwise and vice versa to change it. Now coming to time delay adjustment. The potentiometer at the right side of the sensor is for time delay adjustment. This potentiometer sets how long the output will remain high after the motion is detected. It can be adjusted from 1 second to 3 minutes, that is nothing but 180 seconds. Turning the potentiometer clockwise increases the delay, while turning the potentiometer counterclockwise delays. The PIR sensor comes with two trigger modes, that is single trigger mode and multiple trigger mode, which is L mode and H mode. In L mode, the output goes high as soon as the motion is detected and remains high for a period determined by the time delay potentiometer. When it is high, the further detection is blocked until the output returns to low at the end of the time delay. If there is motion after the timeout, the output will go high again. As you can see in the image, in the motion 3, that is nothing but when there is a motion 2, the pulse will go high for a time delay of t. But before completing the time delay of t, when the motion is triggered at a point 3, see, you can observe that motion is neglected, that is nothing but ignored. Whereas coming to in multiple trigger mode, that is H mode, the output goes high as soon as the motion is detected and remains high for a period determined by the time delay potentiometer, same as L mode. But unlike single trigger mode, the further detection is not blocked. So the time delay is reset each the time motion is detected. That is nothing but, in the picture you can observe that when a motion is detected at the point 1, the pulse will go high for a state of time delay t and comes to the low state. When there is a motion at the point 2 and goes for a high state, even when it is in the time delay of t less than t is in a high state, when a motion is detected, it will be re-triggered and goes to a time till t. Before the time t itself, when a motion is detected at the point 4, it will be re-triggered and goes to a time of t. So the motion will be detected continuously and will be triggering the pulse continuously. When there is no motion for the time delay of t seconds, it will come to a ground state. So this will be useful for the generalized applications when it is in the H mode, that is nothing but multiple trigger mode. You can change the mode of operation from single trigger mode to multiple trigger mode by changing the jumper from H mode to L mode. The PIR module has two solder paths for additional components. These are usually labeled as RT and RL. Note that on some boards, the label may be covered by Fresnel lens on the opposite side of the components. At the RT part, this connection is for a thermistor or a temperature sensitive resistor. Adding this to the PIR sensor increases the accuracy of the detector to some extent. And for the RL, this connection is for light dependent resistor, that is nothing but LDR or a photoresistor. Adding these elements enables the PIR sensor to function effectively even in the lower light conditions. Since the sensor is temperature sensitive, variations in day and night temperatures can impact its accuracy. By integrating these extra components, we can implement logic to enhance the PIR sensor's compatibility with surrounding temperatures, ensuring its higher accuracy. If you want to make this application, please comment them, we will try on it. Let's make the simulation of the adjustments, that is time and sensitivity, by using two potentiometers and display their values. Let us create a circuit based project and change the name of the file to adjusting the functionality of a PIR sensor using potentiometers. Now for this we need an Arduino. Whenever a motion is detected, let's blink an LED. For an LED we need a resistor. Here we are using a PIR sensor, and for placing all the components we need a small breadboard. As we have discussed, we will use a potentiometers. Let's take two potentiometers. One is for time and is for sensitivity. So let's keep the potentiometer and the PIR sensor in place. Let's connect the LED to the 12th pin. And change its color to red, and connect the LED to the pin, and connect the ground pin and change its color to black. Now take the breadboard and connect the current pin, change its color to red, and connect the ground pin and change its color to black. Now here we can see terminal 1 wiper and terminal 2 for the potentiometer. Terminal 1 is for the VCC connection, so let's connect it to VCC, that is down pin, and change its color to red. In the same way, terminal 1 to the VCC. Now terminal 2 need to be connected to the ground and change its color to black. Terminal 2 black, and now we need to connect this wiper pins to the let's make this pin as a potentiometer 1 as a sensitivity pin. So let's connect it to the A0 pin and change its color to orange, and connect the other pin, that is time delay potentiometer, to A1 pin and change its color to, let's say, green color. Now we need to connect the signal part, power and ground of the PIR sensor. Ground is to be connected to the ground and change its color to black. Power pin, that is VCC, change its color to red, and connect the signal part to second pin of the Arduino, that is digital pins. Connect it to second pin and make its color to purple. So we have connected all the connections. Let's go to the code part. I have already made a code for you, so let's paste it here. Here you can observe that we taken an integer variable of PIR pin, that is signal pin of the PIR is connected to the second part of the digital ports of the Arduino. So number 2, LED pin is initialized as 12, that is 12th pin is connected to LED, and sensitivity, that is nothing but one of the potentiometer is for sensitivity, we have connected it to A0, and time delay part, so time delay pin is connected to A1. So we have initialized in the same way. Here you could see commented text for your better understanding. I will provide the code in the comment section and the description part. Now let's go to the void setup. In the void setup you can see PIR pin is an input pin, and in the LED pin is an output pin. Sensitivity is an input pin because sensitivity is one of the input to the processing, and the delay is also one of the input pin, and we need to print the values in the serial mode. So we will start the serial communication with a baud rate of 9600, and let's go to void loop part. In the void loop part we will read the state of that is nothing but whenever a motion is detected, we need to get that from the PIR sensor, and we need to process on it by getting this value to the Arduino. So we will get that information to the PIR state variable as an integer variable. It will it will be recorded as whether it's high value or low value, that is 1 or 0. Based on that we can observe when there is motion or not, and we can get the analog value because a potentiometer is an device which gives its value as an analog one. So we will get that analog value from the sensitivity pin, that is nothing but an input as a potentiometer, and we will get it into the sensitivity pin. And let us take a variable of int delay and get the delay value into the delay level integer variable. Let's make the integer delay level to the long int because its value is way more greater than the expected. So and after that we will use a map function for mapping the sensitivity. As we have already discussed that the sensitivity will be ranges from 3 meters to 7 meters for an PIR sensor. So here in the code we have to keep every value in the centimeters and the time is to be in the milliseconds. So 1 meter is equal to 100 centimeters. So it will be represented as 3 meters to 7 meters, that is 300 centimeters to 700 centimeters. And in the same way for the time delay we will make it to 1000 and 1,80,000 milliseconds. And here you can see whenever the status go to high, we'll make the LED to be into the high state, and we'll print a message like motion detected, and we'll print the adjustment delay, that is nothing but whatever the time we have kept as a time delay, and also the sensitivity adjusted, and the centimeters to be given as a notation. So whenever there is no motion, we will make the LED pin to the low and we will print a no motion message. Now let's simulate the project. Start simulation. Serial motor, no motion is detected. So whenever we make a motion, you could see like here basically a potentiometer in a physical part, we can see like it should be clockwise to increase the value and anti-clockwise to decrease the value. But here in the simulation part we have to keep in the reverse way, that is whenever we make the turn into the clockwise, we will decrease the value and the maximum value in the anti-clockwise direction. So let us keep these values to the lowest part and simulate them again so that you can observe the values here. So that is nothing but 1 millisecond, 100,000 milliseconds, that is nothing but 1 second is the delay we have given, and 300 centimeters, that is nothing but minimum distance, 3 meters is the basic. So when we increase the time delay to some extent, and when we see it is 11,673, that is nothing but 11 seconds of delay we are giving. So after 11 seconds only the detection will be go on and the motion will be sensed. This is nothing but we are working in a L mode, that is nothing but single trigger mode. So basically in a online simulation platform this will be defaultly set to L mode. I think you have a clear picture of this working. Here you can see like we are not dealing with the sensitivity part because as we are in the simulation part we can only see the distance but we cannot simulate them into real extent. So I'd like to give this part to your own observation by using this with a physical sensor. If you have any doubts, please comment them, and please note that this simulation is only for understanding the concepts and the sensitivity part cannot be simulated but made only understand purpose. Thank you.